Hello everyone, welcome to day 10th of my Leetcode challenge, and today's question is count primes. The question says we are given an n non-negative integer and we need to count all the prime numbers that are up till that integer n. So without much ado, let's look at the presentation that I have created for this and let's get started. Let me just take a pen here, count primes, Leetcode 204. What is a naive approach that comes to everybody's mind? You start a loop from I equals to 2 up till n, and if the current number happens to be prime, you increment the count. Pretty straightforward. And what is the approach for writing or checking whether a number is prime or not? You start a loop from 2, go up till I into I is less than that input number, and if your k is divisible by the current value of I, that means it is a non-prime number. You return false from it. Otherwise, if the loop is complete, you return true from it. What is the time complexity of this approach? The time complexity is n log n, because you are doing a loop starting from 2 up till n, and for checking whether a number is prime or not, it takes a complexity of log n. The reason being, you only go up till I into I is less than the input number. Can we improvise on this logic, on this time complexity? The answer is yes, and let's move on to the improvised approach. Sieve of Eratosthenes, he was a scientist, and I'm not sure whether I'm pronouncing him right or not, but what he proposed, let me just explain that to you. Let's create a table up till all the numbers that are there in n. So I have taken 16 as n for one of the example, and let's start the iteration. The first number comes out to be 2, and if the number happens to be prime, we'll delete all the factors of that prime number up till the value of n. So let's get started. The first number is 2 and it happens to be prime. You'll delete all the factors of a 2 up till your upper limit, which is 16. So it deletes 4, you'll delete 6, you'll delete 8, and you'll delete 10, you'll delete 12, you'll delete 14, and you'll delete 16. So let's move on to the next iteration. The next iteration says the number is 3, and 3 happens to be a prime number. And since this is a prime number, we'll delete all the numbers that are factors of 3. So 6 is gone, 6 is already gone, 9 is gone, 12 is gone, 15 is also gone. Let's move on to the next iteration. There is no such number. Next iteration comes 5. So in 5, the number happens to be prime, and we'll delete all its factors. 10 is already gone, 15 is already gone. Great. Let's move on to the next iteration. We got 7, and 7 also a prime number. We'll delete all its factors. 14 is gone. Great. Let's move on to the next iteration. 8 is already gone, 9 is already gone, 10 is already gone, and we have 11. So 11, it happens to be prime, and we will delete all its factors. There are no such factors. Move ahead. 12 is gone. 13, it's again prime. We delete all its factors. There's no such factors up till 16. Awesome. So how many prime numbers are left? 2, 3, 5, 7, 11, and 13, which is the expected result. Now let's talk about the time complexity of this approach. So what you are basically doing, you are deleting every second number in the list. So when the number was 2, you deleted every second number in the list. So that will take the complexity of order of n by 2. When the number was 3, you deleted all the third number in the list. So that will take the complexity of order of n by 3. And when the number was 4, you didn't do anything because it was already deleted. And then comes 5. What is the time complexity for the fifth operation? Order of n by 5, because you deleted every fifth number in the queue. And then comes order of n by 7, because you deleted every seventh number in the list. And this keeps on going ahead. So what we are going to do, we'll take out order of n as common, and what is left is 1 by 2, order of 1 by 2, plus order of 1 by 3, plus order of 1 by 5, plus order of 1 by 7, and so on. So this converges to log of log n, order of n, log of log n. Let me just show the proof for it, and let me show the proof of it to you guys. And this is a divergence of sum of reciprocals of prime, and this shows that 1 by 2 plus 1 by 3 up till infinity converges to something less than equal to log of n plus 1. So rounding it off, we get log of log n. And let's now move on to the coding section. The first thing that I'm going to do is to define a Boolean array that will store the information whether a number is prime or not. And let's just call it number list new Boolean up till n. And let's define another variable count and we initialize it to 0. Let's start the iteration I equals to 2, I is less than n, I plus plus. If my number list of I happens to be false, that means the number has never been marked non-prime. We'll assume it to be prime. The number is prime. Ith number is prime rather, and we'll increment the count. Since the number is a prime number, we'll mark all its factors up till n non-prime in nature. So let's create another loop. Integer j equals to 2, j into I is less than n, j plus plus, and we'll mark number list of I into j as non-prime. We updated it to non-prime. So I into j index or the number is marked non-prime. And let's return the count here. Also, whenever in the outer loop the number turns out to be a number list of I turns out to be true, that means it's a non-prime number and we'll reject it upfront. And let's try this up. Let me just submit it. Accepted. The time complexity that I showed you guys is order of n log log n, and the space complexity for this approach is order of n, because using a Boolean array up till the length of n. Thanks for watching the video. Hope you enjoyed it. Please don't forget to like, share and comment in the section below. Also subscribe to the channel.